Section 10.4 looks at phase diagrams of substances, which is a graphical representation of the substance and what temperatures and pressures the substance is a solid, a liquid, or a gas. On the left, we have a general example of a substance, and on the right, we have water specifically with some of the temperatures and pressures marked out. Also, something that's unusual about water is that as you increase the pressure, the melting point, the transition from ice to water, happens at lower temperatures, whereas for most substances, it happens at slightly higher temperatures as you increase the pressure. So at the highest temperature with low pressures, that's when a substance is a gas. At low temperatures, that's when a substance is a solid, and then we have this Y-type shape, and in between we have when it's a liquid. This line over here, the transition between solid and liquid, is the melting and freezing point and how that is changing. This other line, the change between liquid and gas, is the boiling or vaporization that can take place. And then a line that we could have between solid and gas, going directly to gas from solid, is sublimation or deposition going the other way. So these lines represent what temperature and pressure these different transitions take place. So let's scroll up a little so we can see this graph of, so we can see this diagram of water. And let's see what state water is in at 50 degrees Celsius at a pressure of 150 kilopascals. So we have something over here for the pressure, 150. Maybe over here for the temperature, 50 degrees. And so that is going to be a liquid water set of conditions. Here we're going to look for 70 degrees Celsius, maybe around here, and 0.6 kilopascals, that's already marked off for us over here. So here, we're definitely in the gas section of the diagram. Here we have a temperature of 0 degrees Celsius that's already marked off for us. And if we go straight up, once we get higher than 100 kilopascals, so maybe in this area somewhere would be 200 kilopascals, this would also be a liquid. And finally at 100 degrees, which is already marked off, if we get above 101 kilopascals, so 150 kilopascals would be over here. At this high pressure, even at the normal boiling point temperature of water, it would be a liquid. So remember when we talked about the Clausius-Clapeyron equation, at 101 kilopascals, which is 1 atmosphere, water would boil at 100 degrees Celsius. At lower pressures, water boils at lower temperatures, and at higher pressures, like 200, it would boil at higher temperatures. So at 100 degrees Celsius and 200 kilopascals, water would be a liquid still, or at 150 kilopascals. Anything higher than 101 kilopascals at 100 degrees Celsius, the water would be a liquid. All right, this next question, we want to know what temperatures the phase changes take place if you are at pressure of 70 kilopascals. So let's go ahead and write down that pressure and just scroll down a little bit. So at 70 kilopascals, we'll say that it's a little bit lower than 101. So this melting point is going to be really close to 0. It's between 0 and 0.01, so we'll just say that it's at 0 degrees Celsius for the melting point. And then if we follow this to the transition to a gas, it looks like we are going to be boiling at a lower temperature than 100, maybe 90 or 95. So remember, at lower pressures, water will boil at lower temperatures. So the boiling will be at less than 100 degrees Celsius, maybe around 90 degrees Celsius. All right, our next question is asking whether water is able to undergo sublimation at atmospheric pressures. So atmospheric pressure is this pressure here, about 100 kilopascals. And you can see that water goes from solid to liquid and from liquid to gas. It does not go from solid directly to a gas at this pressure. This area here is where water could go from a solid directly to a gas. So this would only happen at pressures below 0.6 kilopascals. So you have to have quite reduced pressure, like a pretty strong vacuum, to be able to get sublimation to occur for water. So the answer to this question would be sublimation at atmospheric pressure, no. And the pressures needed would be very low pressures, below 0.6 kilopascals. At very high pressures and temperatures, in this upper right corner of the graph, we have an unusual phase that we usually don't come across, called a supercritical fluid. It has properties somewhat in between those of a liquid and of a gas. It is more dense than a gas. However, it can expand to fill the container like a gas, not like a liquid. So the ability to fill the container and expand and be uniform throughout the container makes it a little bit like a gas, but the density and the ability to dissolve things make it more like a liquid. There are some videos linked in Canvas of some supercritical carbon dioxide and what that is like. So I encourage you to go and watch that. And 304 Kelvin, about 31 degrees Celsius, about 90 degrees Fahrenheit. So fairly warm and then substantial pressure. You can get supercritical carbon dioxide. And it has some commercial uses, so that is something that's a supercritical fluid that is actually used. Let's take a look at what phase changes are for carbon dioxide at these various pressures. So at 100 kilopascals, close to atmospheric pressure, CO2 goes from solid to a gas at close to minus 75 degrees Celsius. At a higher pressure of 1000 kilopascal, we can actually get some liquid carbon dioxide. So we'll get solid going to liquid at maybe minus 55. And then liquid would go to gas at maybe minus 40, minus 30 perhaps. So then at an even higher pressure, 10,000 kilopascals, we have solid going to liquid, close to negative 50 degrees. And then if we keep warming it up, we have a transition to a supercritical fluid at around 30 degrees Celsius. So here are the transitions at those various pressures.